Okay, now regarding these cycles, we need to remember some of the important points. So the first point is area of the cycle in PV diagram gives the W net. That means whatever the area is bounded in the PV diagram by a cycle is going to be the value of W net from that cycle. Second thing is all clockwise cycles are power producing cycle. If the cycle is clockwise, if it is going like this direction, clockwise direction, then this cycle will give us a work producing, okay, power producing cycle. And another thing is all anti-clockwise cycles are power consuming cycle. Okay, like refrigeration. In refrigeration, all the cycles are power consuming. That means in refrigeration cycle, you will see, when we study refrigeration, you will see that all the processes are going to be anti-clockwise, because all the anti-clockwise cycles will give negative W net. Okay, that means they will be power consuming cycle. So now all these 3 points will be discussed by PV diagram. Okay, now to produce a cycle, what we know, we need at least 2 of the processes. Okay, we need at least 2 of the processes. Now suppose these are the 2 processes from state 1 to state 2. There are 2 processes. One is from 1 to 2 it is coming, and from 2 to 1 it is going back to state 1. And as it is going back to state 1, it is producing a cycle, because we have said that if the final state and initial state are identical, then it is going to be a cycle. Now area of the cycle is going to be give W net, and all these points are going to be discussed here. Now if we see the process 1 to 2 is going to be expansion process. Okay, we have told this in previous video, that expansion processes are always positive and compression processes are always negative. And we have also said that area under the plot when projected in volume axis is going to give us the work done or negative work, whichever it may be. When we project this plot in volume axis, the area will give us the work done value. Okay, so as we can see, the 1 to 2 is expansion process, that is positive. Okay, now while going back to 2 to 1, it is going to be compression, because volume is reducing. 2 to 1 is going to be a compression. Okay, so area under this thing will give us the negative work. Okay, area under this thing will give us the negative work. Now area under this will be negative and area under this will be positive. Now this is an anti-clockwise cycle. If you subtract this from this expansion process to compression process, then this is going to be a negative one. Here W1 to 2 is going to be less than W2 to 1. Okay, we can easily say it from this process, because for W2 to 1 the area is bigger. For W1 to 2 area is comparatively smaller than W2 to 1. Okay, now so this produces an anti-clockwise cycle. In anti-clockwise cycle, if this is the thing, then W net is going to be W minus W2 to 1 plus W1 to 2. This is going to be negative. Okay, so from here we can say that anti-clockwise cycle is going to give us negative work. Okay, because W2 to 1 is negative, obviously, because it is compression work, so it is negative, plus this is going to be positive. Now as this one is bigger, so the result will be negative. Okay, now if this condition is reversed means, now suppose 1 to 2 is expansion process and 2 to 1 is negative process. Okay, 2 to 1 is compression process. Now in this cycle what happens, here W1 to 2 is going to be greater than W2 to 1, because area under the curve W1 to 2 is going to be bigger than area under the curve W2 to 1. Okay, so after saying that W1 to 2 is going to be positive because it is expanding, this is expansion work, so W1 to 2 is going to be positive, plus W2 to 1 is going to be negative because this is compression work, so this is going to be minus W2 to 1. So this is going to be W net. So W net is going to be a positive one. While it is clockwise, it is giving us positive because W1 to 2 is greater here than W221, and W221 is negative, so final answer would be positive. So from here we can say, and if we subtract this one from this one, okay, if we subtract the area and subtract the area under this curve from the area under this curve, we will get the final area as this one. That means the area inside a cycle. Okay, if we subtract this area under this curve minus area under this curve, we will get the area of the cycle. That means what? W net would be area of this. The first point is concluded by this thing. Okay, we subtract this area minus this area, then we are going to get the area of the cycle, and that area of the cycle is going to give us W net. Okay, second thing is all clockwise. As we have seen, when we have made this clockwise, we have found out positive. While we made it anti-clockwise, that thing was negative. Okay, so all these 3 points is being discussed here. Okay, so now we are going to do some questions from work. Okay, now we are solving this type of questions, so if you concentrate, and this type of questions are very conceptual. If you do this question, you will get to know this chapter better. Okay, so these type of questions are very useful to overcome your confusion, to build the confidence in this chapter. You need to solve this type of questions. Okay, so now let us see what they have given in this question. So they have said that a gas phase above water in closed storage tank contains nitrogen at 25 degrees centigrade and 100 kilopascal. That means they have given that there is a storage contained and there is a water level, and above water there is a gas phase of nitrogen at 25 degrees centigrade and 100 kilopascal. Okay, now a tank volume is 4 meter cube. They have given that whatever the tank is there, where water and nitrogen is there, this is 4 meter cube, and there is 500 kg of water. So whatever the level of water is there, there is 500 kg of water. Okay, now another 500 kg of water is forced. Okay, now another 500 kg of water is forced into the tank. So what happened? At first there was some water in the tank and there was some nitrogen gas. Now another 500 kg of water has been given to this tank. Now forced in the tank, what is the work done on nitrogen gas? That means what they have given, that there is a rigid tank, there is some water level, there is 500 kg of water here. Okay, and above that there is nitrogen at 25 degrees centigrade and pressure is 100 kilopascal. Okay, there is 500 kg of water. Now they have said that they have forced another 500 kg of water here. Okay, now they have said that there is another 500 kg of water here. They have forced. So obviously if you force some of the water here, there will be decrease in the volume of nitrogen. So as there is decrease in the volume of nitrogen, obviously some work has been done on the nitrogen gas. Okay, so what is the amount of work done? That has been given. Now since there is no temperature change is given, that means this complete process is going to be isothermal process. Okay, now let us find the volume of 500 kg water. What was the first volume? Okay, what was the first volume of the nitrogen gas? So for that we need to find the volume of water. So we know that density equals to mass by volume. So density of water we know 1000 kg per meter cube, and mass they have given as 500 kg. So what will be the volume? Volume will be mass by density. Mass they have given as 500 kg, and density is 1000 kg per meter cube. 1000 kg per meter cube. So the result will be 0.5 meter cube. Okay, so at first when the water was there, the water was consisting of 0.5 meter cube, and the total volume of the tank was 4 meter cube. That means what was the volume of nitrogen? That means the initial volume of nitrogen was 4 minus 0.5 of water, remaining is 3.5 meter cube. Okay, so this was the initial volume of the nitrogen in the tank. Now another 500 kg of water has been forced. That means what? Another 0.5 meter cube volume has been occupied. Okay, that means at first there was 0.5 meter cube. Now by forcing another 0.5 meter cube has been increased. Okay, now what is the final volume of the nitrogen? Now the final volume of the nitrogen would be V2. Initially it was 3.5. Okay, now another 0.5 has been forced. So the final volume would be 3 meter cube. Okay, so this is the final volume of the nitrogen after forcing the 500 kg of water. Again, this is the final volume. So now, as this is isothermal process, the what would be the work done? Work done would be nothing but constant into ln into final volume by initial volume. Okay, now constant is P1 V1 into ln is what? V2 is given as 3 and V1 is 3.5. Okay, pressure 1 is given as 100 kilopascal. So pressure would be 100 and volume 1 of nitrogen gas was 3.5. Okay, volume 1 of the nitrogen gas was 3.5. So this would be 100 into 3.5 into ln 3 by 3.5. Now if you do this, you will get the answer is minus 53.95 kilojoule. Okay, we will get this answer as minus 53.95 kilojoule. So why there is minus? Because there is compression. There is compression. Okay, now if they ask what is the work done by nitrogen, then it is getting compressed, so answer will be negative. But they have asked here what is work done on the system. What is, that is after giving the water, what is work done on the system. Now as they have already mentioned work done on the system, no need to take the negative value, you just take the positive value 53.95 kilojoule. Okay, because if they ask what is work done by the system and this is compression, then this is negative, but they have asked what is work done on the system. Okay, so on the system you will take this value only, but in positive number. Okay, so this type of question will help you build the concept of how volume, when volume is compressed, work done is negative, and related to this some other things will be also getting cleared if you solve this type of question. Okay, so this is the process how to solve this type of question. For every process you need to give some new idea to solve this question. The more you practice, the more the chapter will be clearer to you. Okay. Okay, the next thing we are going to discuss is heat. Now what is heat? Heat is a transient form of energy. Transient form of energy means what? If you remember what we have taught in the last videos, transient form of energy is nothing but any energy which can cross a boundary. If there is any energy which can cross the boundary of a system, then it is known as transient form of energy, and which flows due to negative temperature gradient. Now gradient is what? Gradient is the difference of the same property between two different places. So now if you take temperature, if the temperature of certain body in this place is going to be at certain temperature, and in the other side of the body that property is going to have some different value, then the difference of that same difference of the value of that same property, that is temperature, is known as gradient. Okay, and flows due to negative temperature gradient means it always flows from higher temperature to lower temperature. Okay, now the direction it is flowing is always from higher to lower, that's why we call it as negative temperature gradient. Okay, now again we can say that quantity of heat is always proportional to the mass. Obviously, if you need to heat at if you need to increase the temperature of a 10 kg body, it will take lesser heat than if you want to increase the temperature by 1 degree of a 100 kg body. Obviously, in that case, in this comparison, 10 kg body will require less amount of heat. So heat is obviously going to be proportional to mass. Again, heat is going to be proportional to temperature difference. Temperature difference means what? If a body is having temperature of 100 degrees centigrade, then to raise that temperature from 100 degree to 101 degree, it will obviously going to take some less amount of heat in comparison to a body which is having 0 degree centigrade and you want to take the temperature to 101 degree centigrade. Okay, that means if you are having two bodies, one is at 0 degree centigrade and one is at 100 degree centigrade. Now you want to take both this temperature to 101 degree centigrade. Okay, you want that both the body should be having 101 degree centigrade. In that case, that body having at 0 degree centigrade will take much more heat, because the temperature difference here is more higher, and that body having 100 degree centigrade is going to take lesser heat because the temperature difference is lower. Okay, that's why heat is obviously going to be proportional to temperature difference. Okay, now if you combine this, you can say that heat is going to be proportional to product of mass and temperature difference. Now to withdraw this proportionality, we need a constant to multiply. Now that constant would be C. Now what is the value of C? C is going to be acting as Q divided by M into dt. Okay, now this C is known as specific heat. Okay, now if M is equals to 1 and delta T is equals to 1 degree centigrade, M is equals to 1 kg. That means suppose we have taken a body of 1 kg and we want to raise the temperature by 1 degree centigrade. That is temperature difference which we are going to take is 1 degree centigrade. You want to raise the temperature of the body by 1 degree centigrade, then C becomes equals to Q. If both these values are going to be 1, C becomes equals to Q. That means what? C is nothing but a quantity of heat. Okay, now the definition of specific heat would be, if you want to raise the temperature of a body having 1 kg mass by 1 degree centigrade, then the amount of heat which you are going to give to that body will be equal to the C. Now that C is known as specific heat of a body. Okay, so finally we can say that specific heat of a body is the amount of heat required for a body of mass 1 kg to raise the temperature by 1 degree centigrade. That quantity of heat is known as specific heat. Okay, the next thing we are going to discuss is convention of heat transfer. Now what is going to be the convention of heat transfer means how we are going to take positive heat transfer or when we are going to take negative heat transfer. Okay, now from the beginning of the subject we are discussing that our main motto, our main agenda, our main thinking is always based upon how we are going to give heat to a system and how we are going to take out work from the system. Okay, so this is our wish, this is the thing, this is the planning which we have done. That means how much amount of we are going to give to a system and how much work it is going to get back to me. Okay, so giving heat to a system is always going to be positive here. Okay, because this is part of our wish. If you give heat to the system, it may take out some work or it may not give some work, but the part of the wish is always starting with giving some heat to the system. So if we want always to give heat to the system, then it is going to be positive. Okay, now contrary to our planning, if somewhere some heat is going out of the system, then that is considered to be negative, because that is not our wish. Our wish is give heat and take out work, but in place of work is heat is coming out, then it is always going to be negative. Okay, so heat given to a system is always positive and heat coming out of a system is always going to be negative. So this is going to be our convention for heat transfer. Okay, the next thing we are going to discuss is specific heats of gases. Okay, now if you remember what is specific heat is nothing but it is the amount of heat which is required to rise the temperature of the body of 1 kg mass by 1 degree. Okay, now specific heat of gases. Specific heat of gases is generally of two types. Okay, one is specific heat at constant volume and another one is specific heat at constant pressure. Okay, now to understand this we are going to describe it by these two diagrams. Now the first one, which is at constant volume, what does it mean? There are two stoppers given. So even if you give heat, we all know that air expands very highly when you give heat. Okay, so in this case what happens, if you give some heat, the air will expand. By expanding this air, this piston will go up. So after going up to a certain point, suppose this, so after reaching T1, suppose after reaching T1, this piston has touched this stopper. So what happens, after further giving heat, the piston cannot go up. Even if the air tries to expand, then also the piston cannot go up due to this stopper provided. Okay, now and in this case it is constant pressure. Constant pressure means what? Suppose this is also the let us suppose these both system are having m mass of air. Okay, and these both are having initial temperature of Ti. Okay, now let us suppose in constant pressure what happens, after reaching the same temperature Ti, the piston is rising here. Now if you give some heat, if the air tries to expand, then what happens, the piston will go up. But in this case it is not, there is a constant there, these are the two stoppers. But in this case if you give some air, this can go up. So if it goes up, the pressure inside this is maintained. Okay, so to understand very carefully, let us start with this one, that is constant volume, specific heat at constant volume. Specific heat at constant volume, what is specific volume? The amount of heat to raise the temperature of 1 kg mass by 1 degree. Now for this constant volume, what happens, since you are giving heat after reaching Ti, that is T initial temperature Ti, since you are giving heat, it is not expanding. So where does this heat go? We all know for the first law of temperature, first law of thermodynamics, what is energy can neither be created, it is transformed from one form to another. But in this QV, there is no work is coming out since it is constant volume. So what is happening? The total heat is converted to increase the internal energy of this system. Now, if you know, we may have said that internal energy is function of temperature. Okay, internal energy is function of temperature. That means what? If internal energy increases, the temperature increases. Okay, and in this case what happens, if you give some air, the air tries to expand, and this work is also going to get out, because this piston is going up, and this piston is going up is displacing the piston, and we all know, we have found out the displacement work of a piston cylinder arrangement. By giving heat, we are getting some work here, but it is constant volume, that's why we are not going to get any work. So the complete heat is converted into internal energy. But in this case what happens, if you give some heat, some of the heat is going to increase the internal energy, but most of the energy is expanded due to expanded for rising this piston. Okay, for rising this piston, some of the heat from QP is going to be expanded, and internal energy is also going to rise, but for a very small amount comparative in comparison to this one. Okay, so in this thing what happens, since a little amount of heat is trying to increase the internal energy, and as internal energy is the function of temperature, that's why the temperature rise in this case is going to be slower rate, in a slower rate, because some of the energy is expanded to raise the piston. Okay, so in this case you will get the rise in temperature in a very high rate. Okay, because the work is not coming out, and the energy is converting the internal energy, converting to increase the internal energy. But in this case, some of the energy is expanded to raise the piston. Okay, so whatever the energy it was going to convert to raise the internal energy, in this case it does not happen. Okay, because some energy is expanded to raise this one. So in this case, whatever the rate of rising temperature you are getting will be slower than this one. Okay, so what happens, suppose we need to take this system and this system to TF, final temperature. Okay, final temperature. So what will happen, for this system to reach to TF, that is T final temperature, it will take only less heat, because all the heat is converting to internal energy. But in this case, it will take more time to reach the final temperature. Why? Because whatever, only a portion of this heat is going to take place in rising the internal energy, and only the rising internal energy will increase the temperature of a system. Okay, so specific heat is what? It is just the amount of heat. Okay, so that's why what happens, in this case it will take less heat to reach the final temperature, and in this case it will take more heat to reach the final temperature. Okay, so this is QP and this is QV. This is at constant pressure, heat given at constant pressure and heat given at constant volume. Okay, now in the previous video, board which what we have learned that QE is equals to m into C into del T. Okay, this we have learned in previous board. Okay, now for constant volume what will happen, this will become QV and this will become CV, and for constant pressure whatever the heat given, it will become m into Cp into del T. Okay, now from both this explanation what we have seen that QP is greater than QV. Okay, because in this case we need to give more heat to reach the final temperature, so QP would be greater than QV. Now for QP we can write that m Cp del T is greater than m Cv del T. Okay, now in this whole case, mCp and mCv, mass is constant for both the cases, so mass is going to get cancelled out, and temperature difference is also same, because here also we are taking final temperature as Tf and initial temperature as T1. Here also final temperature Tf, initial temperature Ti. Okay, so both this case del T is also going to be same, so del T is also cancelled. For that we can say that Cp is going to be greater than Cv. Okay, so specific heat at constant pressure is always going to be higher than specific heat at constant volume. Okay, and another thing you need to know, for that, for CP includes some of the external work, because the piston is going up, some external work is coming out. Okay, so CP includes some external work as well as increasing internal energy, because some portion is also rising the internal energy of the system. So CP includes both external work and some internal energy increases also there, including CP, okay, consisting of CP. But in CV what happens, there is no external work, only increase in internal energy is there due to CV. Okay, so the final conclusion we can say that CV includes only rise in internal energy, whereas CP includes rise in internal energy as well as some external work. Okay. Okay, the next thing we are going to discuss is adiabatic index gamma. Now what is adiabatic index? Adiabatic index is nothing but it is the ratio of specific heat at constant pressure to specific heat at constant volume. Okay, this is known as adiabatic index and this is written as gamma. Okay, now this gamma value is CP CV ratio. Okay, it is the ratio of CP to CV. CP is what? Specific heat at constant volume, and this is specific heat at constant pressure and specific heat at constant volume. And this whole thing is going to get a value which is greater than 1. Now why is this value is going to be greater than 1? Because it is a ratio of CP and CV, and we just found out that CP is greater than CV. Okay, now for mathematics, if you know that if the numerator value is greater than the denominator value, then this ratio is going to have a value which is always greater than 1. Okay, that's why adiabatic index is going to carry a value which is always greater than 1. Okay. Okay, the next thing we are going to discuss is specific heat for perfect ideal gas. Now if you turn over your notes, or if you remember what I have said in the previous videos, we have said that ideal gas are of two types. One is perfect ideal gas and one is semi-perfect ideal gas. And under that perfect ideal gas, it was written that CP and CV values are constant. Okay, and under that semi-perfect ideal gas, it was written that CP and CV are going to be functions of temperature. Okay, now this is the same thing we are going to tell here. Now for perfect ideal gas, CP and CV are constant. That means what? If you make a graph of CP, CV and gamma versus temperature, what happens with the rise of temperature? CP is going to be constant. If you rise this temperature to a certain value or infinity, you keep increasing, that CP value is going to be constant for perfect ideal gas. Okay. Similarly, CV value is also going to be constant for perfect ideal gas. Okay. Now, since gamma is the ratio of these two constant values, that is CP to CV, it is the ratio of CP to CV. That's why gamma is also going to have the constant value with the rise of temperature. It is not going to depend upon the any other factor other than the temperature. Okay, with the rise of temperature, gamma is going to be constant. Now what happens if we put here semi, that is specific heat for semi perfect gases? What happens? CP and CV becomes the functions of temperature. Okay, they become functions of temperature. Okay, now what happens? CP value increases with temperature for semi-perfect ideal gas. Okay, for semi-perfect ideal gas, what happens? CP value and CV value increases with respect to temperature. Okay, but this gamma, what happens? This gamma is ratio of both these two, but this gamma decreases with this increase of temperature. Okay, now we plot this here. This thing would be something like this. Okay, this is going to be CP and this is going to be CV. Okay, and this value will be gamma. Okay, now if you see, with the rise of temperature, CP value is increasing. With the rise of temperature, CV value is also increasing. Okay, CV value is increasing. Okay, now this gamma, what happens with the increase of temperature? The CP value is decreasing. Okay, now this is the difference between specific heats of perfect and semi-perfect ideal gases. Okay. Okay, the next thing is specific heats of solids and liquids. Now, how these solids and liquids are going to be different from air in terms of specific heats? Okay, now before explaining the specific heats of gases at constant pressure and constant volume, what we had discussed, we have said that air increases, that means expands very highly if we increase the temperature, or if we give heat to the system of air, then it expands very highly. Okay, whereas in solids and liquids, what happens, if you give some heat, so due to this heat the expansion of solids and liquids are very negligible. Okay, very negligible. So for that reason, what happens, the Cp and Cv are going to be same. It is going to be considered as the same case, because whatever work you are going to get in case of constant pressure, that is very negligible. We can neglect that. Okay, now so for liquid, if you take some constant volume, it is going to, if you, even if you don't put the stoppers, this is going to, when you are giving heat and you are giving a piston, even if you don't provide the stoppers here, it will not go up, or even if it go up, it's very negligible. Okay, it is going to be very negligible. You can say that it doesn't go up. Okay, but in constant pressure, you already don't put the stoppers, because you need to maintain that pressure by taking this piston up. Okay, by taking this piston up, you need to maintain the pressure in constant pressure process. Okay, now for solids and liquids, this rise, even if you put stoppers or not, this rise in this piston is going to be very negligible. Okay, that means expansions in solids and liquids are going to be very negligible. So whether it be constant pressure, whether it be constant volume, if you put it like this only, this can be considered as constant volume, because this is not going to go up. This can be considered as constant pressure, because to maintain pressure it is not going to go up, because the expansion is very negligible. Okay, so for solids and liquids, what happens, whether it may be constant pressure or constant volume, the specific heats are going to be same. Okay, now Cp is going to be equals to Cv. Okay, equals to C. Okay, now for water is also incompressible, whether it may be constant pressure or constant volume, this doesn't expand. Okay, for water this value is 4.184 kilojoule per kg Kelvin. Okay, water is a liquid, it doesn't expand with the rise of temperature, it is incompressible also. Okay, so for solids and liquids, Cp is always equals to Cv, because both the case turns out to be same. Okay. Okay, the next thing is that adiabatic index can also be written as 1 plus 2 by L. Now this is nothing but an experimental relation which we have found out, or which the scientists have found out, to find out the gamma even if the Cp and Cv is not given, by reading the characteristics of molecules. Okay, or the degree of freedom of the molecules. Here n is going to be the DOF, or degree of freedom of molecules. Okay, now what is degree of freedom of molecules? How freely these molecules are going to move. In a translational way, how many ways are there? In a rotational way, how many ways are there? To sum that up, we are taking a value of n. By n, we can say that the degree of freedom of the molecules of a particular gas is going to be having a certain value, which is written as n. Okay, now this is completely an experimental value. Okay, now there are gases like monoatomic, diatomic and triatomic. Monoatomic means what? These are going to contain one particular gas. Okay, like helium and argon are the examples of monoatomic gases. Now for the monoatomic gases, this n is going to be equal to 3. Okay, experimentally they have found out that for monoatomic gases, degree of freedoms, the molecules of these gases, the degree of freedom is going to be 3. Okay, if we put this in the same relation, what we will get? We will get that gamma value is equals to 1.67. Okay, my examples, you remember that this is for helium and argon. Okay, now for diatomic gases which are contain particular gases of one molecule, okay, with 2 atoms. Okay, that means 2 oxygen atoms form oxygen. Okay, O2, oxygen plus oxygen mean converts into O2. So diatomic gas can be nitrogen or oxygen, O2, N2, S2, etc. Okay, now experimentally it is found out the degree of freedom of such type of diatomic gases is generally n equals to 5. Okay, now molecules of these diatomic gases can move 5 different ways. Suppose 3 translational ways in 3 directions and 2 rotational ways. Okay, so degree of freedom is going to be 5a. If you put it in the value of gamma, then you are going to get 1.39 or 1.4. Okay, this is going to, now since it is 1.4, we know that for diatomic gas, air also comes under the same category of diatomic gases. Okay, and the next one is triatomic gas. Triatomic gas means what? 3 atoms will form a molecule. Okay, like carbon dioxide, sulfur dioxide. Okay, these are the examples of triatomic gases. Carbon dioxide, what happens? 1 carbon and 2 oxygen. So 3 atoms are there to form one molecule of carbon dioxide. So this is triatomic gas. Now experimentally it is found out that degree of freedom of this triatomic gas is going to be 6. So this may be 3 translational and 3 rotational. Okay, 3 rotational about 3 different axes and 3 translational way in 3 different axes. Okay, now if you put this in the same relation, gamma equals to 1 plus 2 by n, you are going to get the value of 1.33. Okay, now the purpose of this is, even if the Cp and Cv is not given to you, you can easily find this adiabatic index by knowing the gas. Suppose in some questions it is given that for carbon dioxide you need to find the gamma. So carbon dioxide is CO2, that is 3 atoms, that is triatomic gas. You remember these values for mono, diatomic and triatomic. Okay, so after remembering this value, you can easily find these gamma values for different gases, mono, di, tri. Okay, now suppose in question is given that for carbon dioxide what is going to be the gamma value. Okay, so you can find it in this way. Okay, so carbon dioxide containing 3 atoms, it will come under triatomic gas. N is equals to 6. You put it here, 1 plus 2 by 6, you will get the value of 1.33. Okay, we are going to discuss some of the special cases of work transfer. Okay, so we have derived the work transfer for all the processes: constant pressure, constant volume, polytropic, adiabatic. For all the processes we have given the expressions for work transfer. Okay, so from there we have discussed some of the equations like ideal gas equation and something like that, and by using these we have derived the formula of work transfer. Now these are some special cases of work transfer which does not fall under that category where we conventionally find the work transfer. Okay, so let us see the first example. The first example is, there is a rigid tank with this type of arrangement. Okay, so rigid tank means what? What is rigid tank? We have said that rigid tank is a tank whose none of the boundary would be moving. So none of the boundary is moving means volume is always going to be constant. And we have also said that in previous cases, when volume is completely constant, then work transfer is 0. We have said that. But according to this diagram, if suppose there is a battery and in that battery you have installed some motor, and with that motor you have connected a starter. Okay, now if you turn on the motor, turn on the battery, then the motor will start move. If the motor is starting to move, then this starter will also move. Now if the starter is is moving, that means what? There would be some movement in the air. Okay, now with the movement of this air, the temperature of that air will rise. Okay, temperature of that air rise means internal energy of that air is increasing, because we know that internal energy is a function of temperature. So if temperature is rising, that means what? If temperature is rising, the internal energy is also getting rising. Now what is the first law of thermodynamics? According to the first law of thermodynamics, we have said that dq equals to du plus dw. Now this tank is completely insulated, and further you are not giving any heat also. Even if you are not giving any heat, the tank is already completely insulated. Okay, now since the temperature is rising, heat is completely 0. Okay, now temperature is rising, that means there is some change in internal energy. Always there is some change in internal energy. Okay, now since you are not giving heat, that means what? How is this internal energy is getting heated? Is due to the dW. Okay, it is due to the dW, or that means there is some work transfer into the tank. Okay, that means there is, since this is 0, so du plus dw is going to be 0. Okay, that means du is going to be minus dw. Okay, that means what? Some work transfer. If you, the dw, the du is equals to minus dw. Minus dw means you are giving heat to the system. Okay, the work is done on the system. Okay, so we can say that from this equation we can say that there is some work transfer in this system, whether although this is a constant volume process or rigid tank, there is some work transfer. So this is the special case we are talking about. Now volume is constant, work done must be zero. So volume, when volume is constant, the displacement work is zero. Okay, that means the PDV work which we derive all the time, the PDV or the displacement work is going to be zero. Other than displacement work, this type of work can transfer the can cross the boundary. Okay, so this one is a special case. Now another special case is this one. Now these two are the same tank only. This is stage 1 of the tank and this is stage 2 of the tank. So suppose there is in stage 1 you are making one boundary. Okay, now you are completely dividing the tank into two equal volumes. Okay, now in one side of the boundary you are having some gas, and in another side it is complete vacuum. This is evacuated, this is complete vacuum. Okay, now if you instantly remove this boundary between this boundary, if you instantly remove, what will happen? This gas will try to fill that void part. Okay, you know that if a container is in vacuum, it is in complete need of something to fill the vacuum with. Okay, suppose you are taking out all the air from a bottle and you are putting it in a water container, it will instantly fill. This bottle will instantly fill with water. Okay, even if you put it in air and you remove the cap, then it will completely fill the bottle with air. Okay, that means any container with the vacuum part or with some evacuated container is always in constant need of something to fill this vacuum with. Okay, so as soon as you remove this, instantly this gas will expand and fill up the void. Okay, now in this case work done is completely zero. So now we know that work displacement work is what? P into dV. So volume is getting changed, so there must be work transfer, but in this case there is no work transfer. Why? Because in this case, from filling up this gas from here to here, that means from expanding this gas, since it is vacuum, there is no resistance given by this vacuum part. There is no resistance for this gas to fill this vacuum. Okay, so that is the reason there is no work transfer, and this type of expansion is known as free expansion. That is, expansion against the vacuum is completely free expansion, and since no resistance is provided, then work transfer is going to be zero. Okay, and this is also completely insulated. Now in such cases, enthalpy and internal energy remains constant. How? So we are discussing this for case 2. Okay, so if you write down the first law equation for this case 2, this will be dq equals to du plus dw. Now since we have said that the work done is completely free expansion has zero work. Okay, free expansion is zero work means work done is work transfer is completely zero. Okay, and this tank is completely insulated, so this is also going to be zero. So from here you can write that du is equals to 0. That means u is equals to constant. U is equals to constant means u is function of temperature. Okay, now if u is constant, then T is also equals to constant. That means T initial will be equal to final temperature. Okay, so in this case internal energy remains constant. Since there is no work transfer and no heat transfer, internal energy is going to be constant, and since this internal energy is constant, so temperature will also be constant. And another thing is that enthalpy is also going to be constant. Enthalpy means what? Enthalpy is nothing but H equals to U plus PV. Okay, H equals to U plus PV. Now here U is function of temperature, and PV equals to, we can write that U is also function of temperature, and PV equals to MRT. Now M and T are constant, T is variable. M and R are constant, T is variable. Okay, so both of these are completely depending upon temperature. Okay, now we have found out that this is constant, that means temperature is constant. Temperature is constant, so there will also, the temperature will also be constant. Okay, since in both these terms they are depending upon T and T is constant, that means enthalpy is also going to be constant. Okay, so in such cases, in stage 1 and stage 2, whether the gas is expanding, the internal energy and the enthalpy is totally constant and work transfer is completely zero. Okay, so these are some special cases of work. Okay, in the next board we will read about the flow analysis.